Welcome to another Pi Day approximating the number pi coding challenge on this date, March 14th. I should probably be doing this once again on July 22nd, but that's another story for another time. So in this video, I'm going to find pi somehow in the Mandelbrot set, which is really kind of nuts. The nice thing about this is I can piggyback off of a coding challenge that I've done before, coding challenge number 21, the Mandelbrot set. So the Mandelbrot set, if you're not familiar with it, is a special fractal invented by Benoit Mandelbrot, the mathematician, which is a fractal shape, a self-similar shape that appears in the complex plane. Let me give you a quick summary of the Mandelbrot set coding challenge, and you could go back and watch that if you want to see all the code built. But the idea is that the canvas, the window in processing, represents something called the complex plane. And the complex plane is a plane of complex numbers. What is a complex number? So first of all, complex numbers are something I spent a little bit of time talking about in the Fourier transformation series, so you could also go and watch those. And I'll try to refer you to some other videos that talk about complex numbers and so-called imaginary numbers. So a complex number is of the form a plus bi, where I is the solution to the equation I squared equals -1. So you can kind of think of I as the square root of -1. This is also sometimes referred to as a lateral number, but anyway, naming aside, the idea here is that if the complex plane where the x-axis represents the real component, just real, RE for short, and the y-axis represents the imaginary component, then we have all of these points in this plane are of the form x plus y times I. So the Mandelbrot set appears when you take this idea and apply it to this strange equation. So let C be all the possible x's and y plus I, x's plus y times I that's in this plane. And if we take the equation z equals z squared plus c, and we're going to do this over, we're going to start with z equals 0, basically. And we're going to do this over and over again. So we're going to, let's just forget about complex numbers for a second, and let's just say C is the number 2. We're going to say z equals 0, z is 0, squared plus 2. So now z is 2. So this is like z sub 0. Then the next one, z1, would be, what's z? It's 2 squared plus c is 2. So z1, the next z is 4 plus 2 is 6. And then if I say z, this is important because we're going to have to do this to calculate the digits of pi. That's why I'm emphasizing this. Then the next z equals 6 squared plus 2, which would be 38. So this is doing this with just the number 2, which by the way could be one of these numbers, because what that is 2 plus 0i. All numbers in essence are complex numbers, but the real numbers that we think of, the numbers we use more commonly, just have their imaginary component as 0. So this is the idea. Now, what's the deal here? A Mandelbrot set, that weird pattern. So if we do this with any given x plus yi, this number will sometimes go to infinity and sometimes just sort of oscillate around a smaller number. Basically, to find the Mandelbrot set is we look for any numbers, any of these x plus yi's, where when you apply this iterative formula, you get past a certain magnitude. So you can also think of this as a vector, a plus b. And so if we did something like took the square root of a squared plus b squared, the magnitude of this vector, if that magnitude is greater than 2, it is a member of the Mandelbrot set. And when we look at all those complex numbers within a range, you can see all of these black pixels right in here are members of the Mandelbrot set. Now, why do you see these spiky things and the grayscale values? This is because I'm actually specifically counting the exact number of iterations it takes before we get, and I'm saying a squared plus b squared is greater than 4, because that way I don't have to do the square root. And then each pixel color is colored based on the number of iterations it takes and before it escapes, before that escape value, before it gets past 4. Okay, that's the Mandelbrot set. Now, wasn't there something about calculating the digits of pi? So I didn't really know about this. Where I learned about this is from Holly Krieger, a mathematician who appears often in the YouTube channel NumberPi. And there's this video, Pi and the Mandelbrot set, where Holly Krieger goes through and explains this discovery and how it works. And I would really recommend you just stop right now and watch this. Maybe you're going to come back here to see me code it. Maybe you're not, because that's enough for you. I'll also refer you to this page I found on the interwebs here called The World of Pi, which has a little bit more information about this here that I'm also going to want to refer to in terms of this special place, not in the Mandelbrot set, but in the complex plane, 0.25 plus x. So what do I mean? So let's say, so this is our Mandelbrot set. I'm going to loosely draw it like this. It kind of looks like this. This is my crappy, horrible drawing of the Mandelbrot set. If we look at this diagram here, you're going to actually see the values of x and y. So you can see that this is the point 1, comma 0, right? So the point 1, comma 0 is somewhere over here, and it's not in the Mandelbrot set. So the way we're calculating pi is not actually something in the Mandelbrot set, but it is this iterative process applied to a particular location outside of the Mandelbrot set. And there are, by the way, some other locations that you can do this same math to, and that's covered on that webpage. But I'm going to do it not at 1, comma 0, but at 1 1/4, comma 0. So if 1, comma 0 is here, maybe 1, comma 25 is over here. This number, when this formula is applied, reveals the number pi in an interesting way. The good news for us is that this, while a complex number, the imaginary component is 0. So we can actually work this out in a much simpler way. We don't have to do the complex number multiplication, although that's an interesting thing to do, and I probably should have been, I feel like I botched that in the previous coding challenge, so I should come back and do another video about building a complex number class in Java and multiplication, all that. But, so let's just look here. All right, so now that I think of it, I think what I want to do is actually just sort of start over. I could use this code, but we don't actually need to draw the Mandelbrot set to emphasize this. I actually don't need a setup function right now. Let's think about this. What I want to have is my complex number, c, which is really, at this point, just the number 1.25. Okay? So I have the complex number c. It is really a plus bi and the 1.25, but we're simplifying things. The complex number has no imaginary component. Then what I want to do is I also want to have the value z starting at 0. And what I want to say is, the thing that I want to do is I want to say z equals z times z plus c. And I want to do this over and over again. So maybe I want to do it for some amount of iterations. I want to do it while z is less than 2. Because when this eventually gets greater than 2, that's the number of iterations. So I'm going to say int, I want to count the number of iterations, sorry. So each time I'm going to say iterations plus plus. And then let me print line, this is very sad. I should draw it, it'll be more interesting. So let's do size 600, 400, let's say fill 255, text size 32, and text align, center, and text iterations, width divided by 2, height divided by 2. 2, no, this is good, okay, back. So it only took 2 iterations. I just realized I've made a fundamental mistake, but fortunately I haven't gotten too far before I made this mistake. And I remembered now why I'm starting with 1.25, and I should have reviewed this more recently and I wouldn't have forgotten this. But the place that I'm looking at, which is really special, is actually not 1.25 comma 0. It's 0.25 comma 0. Let me actually draw you where that is in the Mandelbrot set in my previous code. So if I want to go to my other code here. And what I want to do is I have this mapping, which is xmin, xmax. So if I want to get a pixel spot for 0.25 comma 0. So I'm going to map 0.25 between xmin and xmax between 0 and width. And then I'm going to get the y value at 0. And I'm going to draw a nice red dot there. So let me say fill 255, 0, 0. And I'm going to draw an ellipse, px, py, 30. Let's make a nice small ellipse. Let's make it a circle. Let's make it a circle. OK. Oh, that's not right. This is y min, y max, yes. And this is 0 comma height. Come on, shiftman. OK. There we go. Look at that. How strange. This is a really, and let's make this much, much smaller. Oh, it's hard to see. Let's zoom on in. This spot right there is called the cusp. So the cusp of the Mandelbrot set, which is a little bump there, is actually 0.25 comma 0. Now, why did I think, oh, I'm supposed to talk about 1.25? The reason is, the idea here is that I'm also going to introduce another variable, epsilon. And epsilon is a little bit of space, or a lot of space, after that cusp. So what happens when I'm a full 1.0 units away from that cusp? Right? And I say the cusp 0.25 plus epsilon. If this is my c, what happens with this iterations? How many times does it take me to escape past 2? So now we could go back to my code, and I can correct myself. And I can change this to the cusp is 0.25, and e for epsilon, I will say is 1. And what I'm really doing is I'm saying I'm really saying c equals itself plus epsilon. So if I do that, what do we get? 2 iterations. So when e epsilon is 1, we get 2 iterations. Now let's go back to this page, this page, and see, look at this. If I have epsilon as 0.01, it's 30. 0.0001, 312. Let's see if we can get that result. Let's try 0.01. 0.01. 30. So what is this? This is 1 divided by 100 to the power of something. That actually kind of reminds me of that whole collisions thing I just talked about. 1.0 divided by 10 to the power, 100 to the power of 1. That gives me 2 digits. Interesting. Let's now create a variable called digits equals, I want 2 digits. This is to the digits minus 1. 2 digits, 30. 3 digits, 312. 4 digits, 3119. No, that's not right. What's the problem? I have very, very, very little precision with floating point numbers. So I didn't get the right result. Let's try changing these to doubles. Double, which you don't typically see in processing, because processing kind of ignores the existence of doubles. I'm going to need to change this to math.pow to use doubles. And now, in theory, 3,140. Is that correct? Yes. So now let's try getting 5 digits. 31414, 6 digits. 314157. In order to test this, I've got 6 digits right now. I've pulled up a text file that actually has the digits of pi in it. So we can see 159, 157. We've got a close approximation with 6 digits. Let's try 7 digits. 141625. 8 digits. Okay, we're getting way off. 143. It's getting worse. So I think we've now reached the limitations of what kind of precision we can have with Java's built-in double. So this is a time where I think it would be worth trying a class that will give us greater precision. So there is something in Java called a big decimal. I can pull up, I'm going to go to the Java 8 docs page. This is the big decimal class. We can see ways of creating a new big decimal. There's all sorts of settings. I can create a big decimal out of a big integer, blah, blah, blah. So big decimal is a class in Java that allows me to have greater precision with a decimal number. So let's try converting all of this. Oh, this is going to be a pain. I'm going to say big decimal. Oh, so first I need to do an import. Import java.math.bigdecimal. So you might not realize this, but in processing, you can import any Java class. I think it's going to be upset with me now, though without a setup function. Yeah, so whoops. So let me just put in a setup function. I don't know that I need it, but let's put that in there just in case. Okay, so now I want to change C to a big decimal. I think I can just do this. Oh, this is going to be kind of crazy. I need to change E to a big decimal. And so this is big decimal 1. That's saved. Divided by, so I need big decimal 100 equals new big decimal 100. And then I would say 100.pow digits minus 1. Is that going to work? Oh, no, dot divide. Dot divide. So I can't use the regular standard operators anymore. OK, so this is E is big decimal 1 dot divide the big decimal 100 to the power of digits minus 1. Then I can say C equals C add E. Big decimal Z starts as big decimal dot 0. This is the number of iterations. I mean, I don't think, do I need a big integer for iterations? I might. I'm not sure. Let's do that. Big integer. Well, let's leave that as an integer for right now. While Z compare to, I have to use the compare to function. If it's less than 2, I think that the compare to function will give me a negative 1. Oh, and this should be a big decimal, the value 2. Z equals Z multiplied by itself, adding C to it. I think I can chain these, and this should be the full word multiply, iterations plus plus. So let me just put this back down to like digits 1. So if I wrote my code correctly, I should still get the number 2. Great. Beautiful. Now let's try to get 2 digits. Oh, this is taking a long time, or I've messed up. So I've just looked into this, and I'm printing the value of Z to 3 decimal places, and I realized it's actually working fine. It's just really slow. Like, it's stuck. It's like hasn't even done the calculation for the next one. I think that what I need to do is, the problem with this big decimal math is it's really slow. And so let me import this thing called java.math math context. And what that allows me to do is create a math context, which is I'll call it MC, which is a new math context. And just to let me just give it to like 5 decimal places, or 10, like a really small math context. Then I think what I can do is I can always put as a second argument to these functions, like divide, the math context. Same thing here, math context. Same thing here. And I think if I do that, it will the operation will be much faster because it's doing less precision. Right? So I got to 30 really quickly. So now I can do 3 digits, and I got to 312. I can do 4 digits, and I got to 3140. 5 digits, 31415. I don't want to have this print line in here anymore. And then let's go to like 7 digits. And we can see we're dying already. So I have figured out a little way to debug this, which is that what I'm just doing here now, I'm trying to calculate 8 digits with a math context of 50. I'm just looking at what that number is with a math context of 50 to 50 places. And it is just taking forever. But I will point out that if I go back to 7 digits, right, I'm trying to approximate pi to 7 digits. And if I take the print line, is really is slowing it down. So if I take out the print line and run this again, I am going to get 7 digits of pi, 3.141591. Of course, the 1 is wrong. The actual number is 2, but I got pretty close. But with only doubles, this is my old code from earlier in this challenge. If I'm trying to calculate 7 digits of pi without big decimal, just with the raw Java double, I'm getting something way more off, 3.1416. So at a minimum, I have, using big decimal, I have improved things, and I've gotten to 7 digits of pi. Hold on, I'm back. I got 8 digits. 314159259. It didn't take that long. 3141592 So you can see I'm close. How did I get 8 digits? Well, thank you to whoever in the chat at HVI said is the nice heuristic to use is digits, the precision that I need is the number of digits I want squared plus 1. So in this case, 65, 8 squared plus 1. Another way that we might watch the progress of this that's a little bit better than just like console logging the value of z is I could move to doing 10,000 iterations or some number of iterations every time in draw, and I quickly just took a break and moved the code from setup into draw. And you can see now with 7 digits, it counts up pretty quickly to that number with 7 digits. There we go. I should make that much bigger. Let's make the size 64. So this is 7 digits. It might be nice to visually just to have the counter go up in a more interesting way. But now we could watch if I go to 8 digits. And I probably should number format this so we could see when we're getting close to the end. For example, if I say number format the number of iterations as 8 digits, or the number of digits, we can see how close we're getting to the end, because at a certain point, this last digit, all that last digit has to do is get to 3. So I'm gonna just leave. I should just leave this live stream going all day. Hold on, well, that would be crazy, right? What if I just left this streaming, change this to full screen, and put it to 11 digits? And I should also put the Mandelbrot set in the background, probably, right? I loaded the image of the Mandelbrot set. I put it in the background. I set the digits to 11. We're going to let this run. I don't know how long this is going to take. There's a big problem with this. I am using integers to count the number of iterations. And guess what? There's not enough integers. We're going to overflow the number of integers the computer can store in the int data type. So I definitely could fix this, I'm pretty sure, by making this a long, which gives a lot more space, probably about 19 digits worth, which is more than 11. But I think just for consistency, let's use big integer. So if I use big integer, and I say it is big integer 0 to start with, then I can also import big integer, and I can say iterations.add, iterations equals iterations.add 1. I guess I probably need to say big integer 1. Let me stop this from running. So this would be increasing the number of iterations. And then, so then I want to take string s equals iterations to string. This will convert it to a string. And then I could do something goofy here, where I could say s equals s dot substring, the first digit, 0, 1, plus period. This is just to make it look more like pi. And then s dot substring 1 to s dot length. Oh, whoa, no, this is bad. I need extra digits even for when it hasn't gotten that high. I could say int difference equals the number of digits minus s dot length. And then I could say s equals, if I add another 0, right? If I just add one more 0, Like I get that. So then I could just add the number of zeros. 4 int I equals 0, I is less than diff, I plus plus. And then this, I could add a certain amount of zeros. And is that 11 digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I think that's right. Okay, that was ridiculous. Well, if you made it to the end of the video, you've now seen my Mandelbrot set processing sketch running and counting the number of iterations for a very small epsilon next to a certain location in the Mandelbrot set. So I really needed a lot of stuff for this. I needed big decimal, big integer. I'm going to let this go now to try to get 10 digits after the decimal, or 11 digits total, including the 3. It's probably going to take about 12 hours. So that's going to be in a live stream that's just going to be a 12-hour live stream of it running, which I will link to in this video's description. We'll see if that works. We'll find out. But thank you. If you have an idea for how to visualize this in a different way, to illustrate the idea, to explain how this works with the Mandelbrot set, maybe there's a more beautiful way to animate it, to connect the concepts of how this is working with the visual result that the viewer is watching. I would definitely encourage, and a big thanks to the number file video and Holly Krieger for that wonderful explanation which led me to do this. I would love to see your version of this. Maybe there's a way you can optimize this to get more digits more quickly. I don't know. I would love to find out. So look at all the references that I'm going to link to in this video's description, and share with me your ideas at thecodingtrain.com, and see you in the future. See you next Pi Day. Oh my God. Oh my God, I'm really stressed out. Three, 1, 4, 1, 5, 9, 2, 6, 5, 3, and of course the last digit will be incorrect because it's an approximation.